All right. So we covered the basics about the big data and also why we need that. So just want to give you several examples of how big data can be used in the AC industry. So I listed links here. It shows that how big data was used to inform better engineering design, like a evidence-based design, like driven by the future user behavior. But I really want to show you this. It's very interesting. Oh, sorry, I thought I was sharing my screen. Yeah. So this is actually what I was talking about. I included some links that lead you to the examples that how people are using big data to inform their design. But I want to show you this quick example, very interesting one called the Google Flux Metro. Have you guys heard about this project before? So it was something called the Google X project. It was an internal secret project inside Google, and for example, like the driverless car from Google, and also the robotic program later sold to the Boston Dynamics. That was also part of the Google X project. So this was also one of the Google X project. What you see on the screen here, that's all the building codes and the fire codes, okay? So the idea is to collect all the building codes for a region, like from a city, and run the machine learning model to understand, that's called a natural language processing, right? To understand the logic and then generate the design by itself. So we're not using any kind of human design. We're just basically using machine learning to learn the building codes and generate design. And there's a very interesting example showing that for this building, basically all the building codes define all the constraints, like the restriction on the head of the building and everything. If you define this interesting cylinder type of thing, it's based on the look of the building, but also all the engineering requirements. And what's interesting is inside it, in the middle of it, do you guys see this is actually open in the middle? Do you know why? Because there's a tree based on the GPS data, based on the satellite data, there's a tree right there. And according to one of the requirements for a tree that is bigger than certain size, you cannot remove it, you cannot cut it. So this machine learning model is so smart, it actually builds this kind of interesting, cylinder structure with an open in the middle and the tree is right in the middle. And more than that, this algorithm actually built a curved wall can give you a good view to that tree. So now imagine that the entire system is automated. And this is a quick video to show how it worked.
Great to hear the really authentic and thoughtful answers from the Keen co-founders. And Rose's talk made me want to be a better human being. And I can't say I've ever given Bayesian statistics a second thought, so that's very exciting. Anyway, today I'm going to be talking about data, and it's actually the built environment. So I know we have a lot of software folks in the room, and to preempt any confusion, I wanted to point out that I'm going to be talking about the built environment with a T. So I'm talking about buildings, roads, infrastructure, not the build environment, which is, make files, environment variables, continuous integration, and whatnot. So at Flux, one of the problems that is top of mind for us is the idea of urban population growth. Right now, we have about 7.2 billion people on the planet, about 50% of which lives in urban centers. By 2050, so just 35 years from now, the world population is expected to grow to somewhere between 9.5 and 11 billion people, according to the UN Population Division. And of that 9.5 to 11 billion people, about 70% is expected to live in cities, which is a huge increase from our 50% figure of today. So if you do the math, that means that we're going to increase our urban population by about 3.3 billion people, which nearly doubles our urban population right now. So, already we struggle to house people in cities. In some places like San Francisco and New York, this manifests as like crazy rents. Like, who here doesn't think San Francisco is just ridiculously expensive? And in other places, less developed areas, this manifests as many people living in substandard housing. So, I'm sure you've all seen the gut-wrenching images of Indian slums, Brazilian favelas, and whatnot. So, just to put some numbers around it, I put together these 3 scenarios. So if we want to house 3.3 billion people by 2050, this is to calculate the number of buildings we need to build. So I have 3 scenarios. One in which we house 100 people per building, one in which we house 250 people per building, and one in which we house 500 people per building. So under these 3 scenarios, we have to build 33 million, 13.2 million, and 6.6 million buildings, respectively, for each of those scenarios. This is a lot of buildings. And just to take it a step further, to express it in another way, to house these 3.3 billion people, we have to build, these numbers here on the right are how many buildings we have to build each day, every day, for the next 35 years. So these are some stunning figures. So if we house 100 people per building, we have to build 2,600 buildings per day, each day. 250 people, 1,000 buildings per day, 500 people, 500 buildings per day. So this is a lot of buildings. And to top it off, today, building operation accounts for more than 40% of all overall energy use in the United States. So not only do we need to find a way to house 3.3 billion people, but we need to do it in such a way that we don't wreak havoc on the planet. So this is clearly a major problem, and one of the reasons I co-founded Flux. So Flux grew out of Google X, which is a research lab at Google dedicated to moonshot thinking. They try to identify the world's most pressing problems, and they put a team of smart people on it and ask them to propose solutions that can be implemented within a 10-year time frame. So Google X is an incubator. Projects don't live forever. They're once mature.
So let me fast forward. I was not intended to play the entire video. So let me see if I can.
Of the stair design. And what's really neat about this is because all of these rules are encoded within this building seed, I can make changes to the building. So here I'm going to request to move one wing a little bit to the west. And when I do that, the building regrows. You can think of it as requesting a new tree to be grown out of a seed. Here it's moving back. And everything just automatically regenerates. So clearly you can get a lot more leverage.
Here she's showing that, you definitely can just give the fundamentals, the fundamental design of that. And then this program is reading all the building codes requirements for different structures and then generate the building, which they call a generative design. I want to see if they can show. Now, this part shows that
where it comes from. So we wanted to build this idea of transparency. You can also use this as a research tool. So imagine you want to build a high-tech co-working space like.
Okay, so I want to show you this quick example. It shows that the metrics, like the maximum building coverage, maximum building impervious coverage, floor area ratio. Those things were not manually tapped into the program. It's just that they basically send all the building codes to this program, and after about 1 hour, this software, this algorithm understand what's going on and tabulize all the requirements and generate the design automatically. So that's an amazing idea, and their ultimate goal at that time was to reduce the design costs, including architectural design, engineering design, and mechanical design, to about only $150 per building. So they're going to make a lot of your work worthless. And so guess what happened to this Google Flux? Now, if you search flux.io, like a Google Flux Metro, it's gone. Nothing happened. Do you know why? It's a smart idea, such an amazing idea. Let me tell you, actually a couple of years ago, I think it was 2017, and actually I invited the CEO, the former CEO of this company, Nick Chim, to give a keynote talk while I was at A&M. So we were having that kind of a construction technology symposium. So he was the keynote speaker. And he told me that the problem is not machine learning. The problem is still human errors. So the thing is, out of the 100 plus building codes and FAIR codes published in downtown Austin. So they basically made this model for downtown Austin. That's downtown Austin. they discovered thousands of conflicting places. So it's kind of like one building code is telling you to do something, the other building code is telling you to do a totally different thing. One building code says, oh yes, you can do this, but the other one says, no, you cannot do this. That's human errors. They had to spend $1.5 million to hire a lot of civil engineers like you guys and also architects to manually correct all the errors and confirm with the city. And that's already more than 50% of the development cost of this algorithm. So they just figure out it's impossible to apply this thing anywhere because of human errors. And guys, that's which way? That's actually the last way, the veracity. We are still the bottom line of the game because we are human beings, we're committing errors. So the data we are generated also bears than errors. So that's why we still need a smarter algorithm that is more robust, that is more tolerant with human errors. Make sense? So I think this is a very interesting example. When I first learned this several years ago, I was so excited and I was thinking, oh, this will be the future. But then only after several years, it was totally gone because we killed it. The human error killed it. All right. So with the rest of today, I think we still have about 10 minutes. I will try my best to show you something, why big data is important. And I guess this is very abstract. I will try my best to interpret that, to explain that. So bear with me. The reason we are needing big data is actually related to how we know and understand the world. This is how we build models. So all the things you are learning, for example, your structural engineering knowledge, your analytical knowledge, that's all models to understand the world, to model the world, to predict the behavior of the world, so we can better optimize our actions. Make sense? So let's see this one, this bluish fuzzy blue shows how the knowledge, the entire knowledge look like, how the behavior of the entire world look like. So number one we do is we do have a boundary. Within the boundary, that's everything we know. Outside the boundary, that's everything we don't know. We don't know yet, right? So let's say within the boundary, that's everything we know. So how we build science, how we understand, the world, it's kind of like we observe everything. For example, you perform some structural material test. You basically comprise the concrete cylinder. You observe many, many times until you see repetitive patterns, right? You see the repetitive patterns, you build a model. Make sense? So based on the observations, we build a model. And then guess what? You will use the model somewhere. So, there are two different phases, induction and deduction. Make sense? So basically we induce something from the observation and we deduce that, right? So basically predict and try to apply that. That's how we understand the world and how science and engineering works, right? Unfortunately, all models are wrong, but some are useful. So we cannot say the models we have today, like the structural, the material models, for example, are not, the material models are the truth. No, they are just a great way to somehow describe the observations, but of course they are not the truth. So we have been struggling to develop better models, and the model can generate prediction that is more and more closer and closer to the observations. Make sense? So let's say you use the material model to predict the performance of a concrete cylinder. It will always be off. But we can develop better and better model to make it more and more close to the final observation. Make sense, guys? So what is the best way for us to do it? Adding more variables. So for example, if I want to predict the stock market price, originally I could just use the GDP, right? The economy, right? But then think about that. If I add unemployment rate, which party is in the office, the population growth, the news, and the oil price somewhere, blah, 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 blah. If I add more factors, can we increase the accuracy of our prediction? Very likely, yes, right? So if we add a lot of information, definitely will make the model more accurate. That's exactly what we do in engineering. I give you this example is the numeric weather prediction, the weather forecasting. Today, you guys, if you open your app, right? So the weather prediction, you can see how many days? Like for the entire week, right? So you can basically see like a week prediction. That was unimaginable just 10 years ago, right? So the numeric weather forecast actually started in 1922 when people tried to use some parameters from the observations, from the climate observations to make a prediction of the weather. The first try was in 1922 and we only used 10 parameters. But in 2018, nowadays, we are using more than 2 million parameters. And that's actually the most popular weather forecasting system called the Global Forecast System, GFS. And with 10 parameters in 1922, the first guy, Louis Richardson, could only forecast the weather in about 6 hours. And that would take him 6 weeks to do. So it actually took him 6 weeks to predict 6 hours of the weather. And the error is 100 times of the magnitude. Okay, so that's ridiculous. But nowadays, the GFS could forecast, 9 kilometer range, 128 layers. 128 layers means, different altitude, the weather, up to 16 days. And to generate that kind of high fidelity prediction, it only takes about 3 hours. And this one actually shows from this 1950s to now, the amount of data processed per day to run this global weather prediction model, and this is, by the way, this is not a regular coordinate, this is log coordinate. So every increase is actually 10 times data. Make sense? So it works. It works also in machine learning. I'll give you this quick example called a classification example. So if I want to categorize if this is a cat or dog, I develop something called features. I mentioned that, right? So let's assume you have 2 features. One is the size of the face and one is the position of the ear, for example. And then if you plot all the pictures in this 2-dimensional space, you basically have one data point. So one data point shows one picture. Make sense? Because I extract just 2 numbers from the picture. And I label them. That's called a supervised learning, right? I think we discussed that. So I label them, let's say all the red colors are cats, all the blue colors are dogs. From this picture, can you find a line or whatever to cut through the data to separate the red from the blue? It's very difficult, right? But if we add another dimension, for example, the weights or the size, the total size of the picture. So that's the 3rd dimension. Then it could be possible that what we see here is actually look like this. It's a bell curve, and the blues are more at the peak, and all the red are more at the bottom. Make sense? So now is that possible for you to just plot a line or a plane to separate the blue from the red? It is possible. Make sense? So it's working. By adding more variables to our knowledge, we can always have better prediction or better knowledge. So that's why for an expert, if I ask you to assess the health condition of a building, you tend to ask a lot of questions. You want to ask the year, the age of the building, the material of the building, the construction methods of the building, the foundation type of the building. The more you have, the better answer can give. Make sense? That's actually, you are building this classification model in your mind to separate this building from good buildings to bad buildings, right? All right. The answer is no. Just recently, people, not recently, maybe about 3 decades ago, people discovered a very interesting phenomenon. So X means the number of variables you considered in your classification model. Y is actually the classification performance. Yes, by adding more and more variables, you actually increase the performance, but there's a turning point. After a turning point, the more you add to it, the worse the performance is. What happened? We don't know. until this guy found this phenomenon called the curse of dimensionality. The curse of dimensionality means if you add more variables to your mathematical model, like y equals f x1, x2, all the way to xn, if you add more xn's, then after a certain point, your model will become crazy because of some mathematical feature of a high dimensional space. Everything will be so different. And this guy, Richard, that's American, he was an American mathematician. He used the word curse of dimensionality to describe that. I'm just going to go over it very quickly, and so you understand what I mean. The number one is the coverage of your data. So for example, now I want to sample, something to run a good model. I want to have a 20% coverage. If I only have one dimension, like one x in my formula, that's easy, right? I just need a 20% amount of data. Now, if I increase that to a two-dimensional space to still have 20% coverage of the entire data, for the first x, I actually need about 45% of data. And for the second x, I also need about 45% of data. That will give me about 20% of the entire area size. Make sense? So think about that. If I want to test, your socioeconomic performance, and if the only variable I have is your gender, so maybe it's easier, right? But now I also consider your education history. So now, in order to still have the similar representativeness from your data, I need to exponentially increase the sampling on each dimension. Like for example, education, and also your, let's say your your work, like your job type, right? And if I increase to 3-dimension, again, in order to have 20% of coverage, now I need to sample about 58% on each x. So the number requirement will increase dramatically. And more interesting than that, so this one, I'm actually plotting this 2-dimensional circle inside this 2-dimensional cube. So let's say which data you want to sample from, the data in the middle or data at the corners. Of course, the data in the middle, that means the representative data, not the outliers. So now if I send it to 3-dimensional, I want data to be from the center sphere, right? Now, check what's going on. When I increase it from 2-dimensional space to 3-dimensional space, the central area or the central coverage is actually shrinking. The corners, the area, the volume of the corners are actually becoming larger. What happened if I increase to 7-dimension? So this is actually how a 7-dimensional cube and a 7-dimensional sphere look like. The 7-dimensional sphere still looks like a sphere, but the cube looks like this ugly thing with 123 corners. And about 97 space are actually at the corners. What do I mean? Pretty much all the data you sampled from your data pool will be outliers. They are not representative at all. They are outliers. Make sense? And another interesting thing, and this is the most bizarre thing, most weird thing I have ever seen. When you increase the dimensionality, there's no near or far. So if you just randomly pick 2 data points, the distance will become equal. So you're basically losing the distribution information if you are sampling in a high dimensional space. So I'm going to talk more in detail later since we are running out of time. But what I want to say is, because of the curse of dimensionality, because of the weird behavior of high dimensional data, we are having this bloody fact. This is the sample size. This is the number of variables. And this is the model accuracy, the performance of that. Yes, if giving certain sample size, you increase the number of variables, the prediction or the performance of your model will increase. But after a certain point, it will decrease. Okay? The way for you to cure this one is to, guess what? To increase the sample size, because we don't want to decrease the number of variables. Why? The number of variables means our knowledge. We know what are relevant. We know what are important for us to understand the behavior of this building. So we don't want to give up on all the knowledge we have. But still, in order to predict the performance of the building, up until a certain point, if I have too many variables, I need even more sample sets to support that. And that sample size means what, guys? That's the big data method. So now we are reaching a point here. Let's say we are going here. Now we have a lot of knowledge, but we cannot go further this way because we know that our prediction, our performance will decrease. Now we have to go a different way to get more data. That's why we are in an urgent need of big data. So I will try to explain more the logic behind this. I hope this will help you understand, why big data analytics represent a new research paradigm and also new management paradigm. I'm sorry, I just figured out I ran out of time. See you guys next week. Don't forget your first team assignment, the Facebook timeline technology review. All right. So see you guys and have a good night.
Thank you, Doctor.
Thank you, Doctor.